Okay, so if you remember the story we've talked about so far, we've got data that comes in. We sort it into different kinds of data that it is. So categorical, quantitative. Okay, so quantitative we can turn into histogram. There's different types for both, but histogram is the important one. I ask you to describe it. You're going to tell me the shape, the center, and the spread. Okay, so once you have described a histogram, what you're doing here is you have a pile of data. That's what we're describing. It's called a distribution. We're turning it into this picture that we can understand. Well, today what we're going to do is we're going to compare information from two different histograms. And we're talking about the position these are in relation. And so here's what I'm getting at. I could be the admissions counselor at a university and I've got one spot left, one student left to get admitted. And I have to pick between a student who took the SAT and a student who took the ACT. And if you think about that for a minute, these have very different kinds of score. ACTs are 12, 14, 32, whatever. And their means and standard deviations are different. The SATs are 1400s, all that. So what do? We can pick only one student, but they're from different histograms. They're from different distributions. So what we need to try is to compare these things in an apples to apples way. And right now it's not. It's apples to oranges. So we use this formula called the z-score. If you put in the score on the ACT of my first student, the mean for that student and the standard deviation, and I crunch that, I get a new universal score. It's the score that's going to be for any situation. So I run both of them through this equation, and I'm going to get numbers that are universal and can now be compared. So for instance, what I'm saying is I run the first student through, he got a 2.0. The other student got a 1.7. Well, what does that mean? It really means how many standard deviation steps they were from the mean on this new universal scale. Okay, so one person was 1.7, the other one is 2. Okay, so if you think about what this is saying, 2 standard deviations better than the average on a test is better. This student did better on their college prep exam than this student did. They did 2 steps better than the average person. So this person should be who we'd select. Now, what if it was, though, you can have steps of, you could do better than average or you could do worse than average. So suppose we crunch this again and we had gotten numbers like this. We're taking the better student. This student was 1.7 below average and this one was 2 below. Do you see that this one is now better? So what I'm getting at is you're allowed to have negatives. They'll always be somewhere probably between maybe -4 and +4, but that's how you could compare them. They're no longer in 2 entirely different systems, they're in one. Okay, you got 2 people shopping at a supermarket, and we're interested in comparing how the wait times are at these 2 different stores. And I'm not sure, this one is supposed to be down here. So somebody had to wait 7 minutes, the other one had to wait 1. So how do these compare? It's 2 totally different stores. So let's see. Actually, these numbers are pretty bad because it's obvious what the answer is going to be, but this is how you do it. So at the first store, this person waited 7 minutes. Here's the average. They waited one standard deviation above average. So this is average, the universal average, and they were 1 above. The second person did it. We crunched their wait time, the mean. They were -2. So they were well below the average rate of wait. So even though it was 2 different stores, we now have this on a universal scale, and we see this student, this person, had a much shorter wait at the grocery store, which we could have figured out anyway, but it's now on the same scale, and we can make sure that comparison is apples to apples. Now, there's a lot of slides in here about the empirical rule. It's super important, but I push it back to a later point in the course. It's the same as this thing called Chebyshev's inequality. I hope you don't see questions about this in my math lab. You shouldn't yet. Okay, now we've got something called a weighted mean. We've got 2 more items here real quick. We've got something called a weighted mean. And you've been doing this whenever you do your grade point average. What you do is you said, okay, I got an A. That was worth 4 points. But it happens at different frequencies. Like this was a 3-hour class, so I can't just do 4. I have to do, it's as if it was worth 4 plus 4 plus 4. You see what I'm saying? One for each hour. You do all your classes, you add that all up, and you divide by how many credit hours you have. Well, this is how we're going to do a very similar idea with, for instance, this example is the number of movies. Put this in list 1 on your calculator, and then put the weight at which these things occur in list 2. So now you're going to find a weighted average. I can't simply say 0 plus 1 plus 2 plus 3, 4 divided by 5 because they occur at different frequencies of time. So I put these in. This is the occurrence, the frequency at which they occur. I run one variable stats, but this time I'm going to say L1 comma L2. Or if you have that little chart that appears, I'm going to say L1 and the frequency is L2. Now, when you get that number out, I shouldn't have come here yet. Oops. When you get that X bar out like you always would, that X bar is now a weighted mean. It takes into account the fact that these things happen at different frequencies. Okay, now we can do a very similar idea with something called group data, where let's try to find what the mean is for this. The problem here is that there's a different number of students and we have these intervals going on. So what you would really want to do if you were finding a mean for group data, what you would want to do is you would add up all the scores, divide by how many you got, but we don't know them. This only gave us a frequency table. The pile of histograms are in a frequency table and they're not individual scores. So let's do a trick to try to get an estimate. I don't know what was put into this basket, but let's just use the midpoint as a good estimate. Now, if you understand what I've been saying, I don't like that this ends in 0.5. I'd want it to be 0.49, 0.49 all the way down here. But what you do is take the two lower class limits, add them up and divide by 2. That's going to get you the midpoint. Take the next two lower class limits, add them up, divide by 2, get the midpoint, all the way down. Now, what have we done? We have a pile of midpoints now. And is it going to... So we have all the midpoints. And there were this many of the numbers. If you went back to the original table, there was one number in that first basket. There's 0 in the next basket, 4, 4, 2. This is our best guess at what's the middle of that bin, that basket. But there was one number in that basket. There were 4 in this basket, 4, 2, so on. And here is a way to get a guess at what the mean would be off a frequency table that doesn't have all the individual numbers available to us. So what you could do is you could put this in list 1. You could use that frequency trick again. You put the midpoints in list 1. You put in list 2 this time. You put the number of occurrences on the frequency table in list 2. You do your weighted mean, your one variable stats with L1 comma L2, and you would get, this is doing it by hand, but on one variable stats, if you use L2, you would get this. Okay. Okay, there's a couple examples here that you could try. So again, I don't like it's ending at 0.5, but you go lower to lower, add those up, get your midpoints, put this in list 2. So your midpoints will go in list 1, your numbers of students in list 2, number of teenagers, then you'll use the one variable stats. So on that list, you're also going to be able to get the standard deviation of this display. So here's your mean, that frequency table of that. We've got a guess at what the mean is for that table, and you also have an estimate of what the standard deviation would be. So I hope that made sense.